In this video, we'll first discuss kinetic energy and then a principle called the work energy theorem. So let's start with kinetic energy. In the last video, I indicated that kinetic energy is the energy associated with the motion of a system. The equation for kinetic energy is 1/2 mv squared, where m is the mass of the system and v is the instantaneous speed of the system. And since this is an energy, then the SI unit for kinetic energy is, of course, a joule. From the equation, we can deduce a few facts about kinetic energy. First, because v is a speed and not a velocity, there's no directional information associated with kinetic energy. The previous video already pointed out that energy in general doesn't have directional information associated with it, but it's worth pointing out again here. The next fact also comes from the speed. Because this is an instantaneous speed, then this equation gives us the instantaneous kinetic energy. And the final point is that because the speed is squared and the mass is always positive, then kinetic energy is also positive as well. Now let's move on to the work energy theorem. The work energy theorem is basically a statement of the conservation of energy. The change in the total energy of a system is equal to the amount of energy added to or removed from the system. This must be true because we can't create or destroy energy. We can only convert energy from one type to another. So the only way that the total amount of energy within a system can change is if energy is added to it from a source outside the system, or energy is transferred from the system to something outside the system. Mathematically, we might write it this way, which says that the change in the total energy of the system is equal to the net or total amount of work done to the system. At this point in the course, the only energy of the system that we've discussed is its kinetic energy. So we can replace the change in the energy of the system with the change in the kinetic energy of the system. This equation is called the work energy theorem, where delta KE is the change in the kinetic energy of the system, and W net is the net or total work done to the system. We will actually expand the work energy theorem into a more complete statement of the conservation of energy after we have discussed potential energy, and then we will expand it further when we discuss rotational motion. The work energy theorem is still a powerful and accurate tool to solve certain problems, and we will first learn how to solve problems with it. It is important to apply the equation correctly, so to help you with that process, I recommend the following procedure. First, as usual, draw a diagram. In the diagram, include the coordinate scheme, identify the system, mark the initial and final locations of the system, and include any applicable vectors. Next, apply the work energy theorem equation and solve for the unknown. And finally, check to make sure your answer is reasonable. To demonstrate this procedure and the use of the equations, I'll work through a simple example. A person throws a softball with a mass of 180 grams straight up into the air. When the ball leaves the person's hand, it is 2 meters above the ground and has a speed of 9 meters per second. The ball then travels up and straight back down to the ground. The net work done to the ball by the air resistance over the entire path is -1 joule. What's the speed of the ball just before it hits the ground? So the first step is to draw the diagram, where we must show the coordinate scheme and identify the system, which we'll define as the ball, and show its initial and final locations, and then show the pertinent vectors like the initial and final velocities and the displacement and the forces acting on the system, which in this case are the air resistance force and the gravitational force. I've drawn the air resistance force pointing down as it would be initially, but as the direction of the ball's velocity changes, so will the direction of the air resistance force. The force of gravity will point down the entire time. Now we'll apply the work energy equation, where the change in the kinetic energy is final minus initial, and the net work consists of the work by the gravitational force and the work by the air resistance force. We know these are the two work terms because these are the two forces that are acting on the system. Then we can expand each kinetic energy term into 1/2 mv squared, so 1/2 mv final squared minus 1/2 mv initial squared. In the problem, we're given the value for the work done by the air resistance. For the work by the gravitational force, we are permitted to use the equation force times distance times the cosine of theta because the gravitational force is constant, which is a restriction on this equation. Next, we can recognize that the gravitational force is mg and the angle theta, which is the angle between the force and the displacement, is 0. Notice in this case it doesn't matter what the sign of the force and the displacement are because just magnitudes go into the equation. Ultimately, the sign of the work comes from the cosine of theta, which is just +1 in this example. We can then solve this equation algebraically for the final speed and plug in values. So we find that the final speed of the ball is 10.4 meters per second. So that's it for this video. We'll continue to discuss energy in the next few videos. So see you then.